video, we're going to discuss the derivative and how it relates to the economic concept of demand. So the general idea behind demand is we're comparing the pricing for a product to the quantity that people are willing to buy. So in general, there's an inverse relationship between those two values. So what that means is at lower prices, people are typically willing to buy more of a product, but as the price increases, in general, people are willing to buy less of a particular product. So producers want to price things high because in general they make more money. Consumers want things to be priced lower because they're more willing to buy things at lower prices. So demand expresses the relationship between how pricing changes and how much people are willing to buy. So retailers and manufacturers, the actual producers of a product, are interested in how small changes in price, typically increasing price, how those small changes are going to impact the demand for the product. So in other words, if the idea is we want to make more money, typically we want to charge more, right? Well, we need to analyze what's going to happen to how much people are willing to buy, assuming we do increase the price. So we want to make more money, we want to charge more, but if people are no longer willing to buy as much, well, how's that going to affect revenue? How's that going to affect the bottom line? So in order to analyze how quantity demanded changes as we change the price, as we decrease the price or increase the price, we discuss what we call elasticity of demand. So is the demand elastic or is it inelastic? So elasticity of demand is defined as the sensitivity, how sensitive, how drastically affected, the sensitivity of demand to changes typically increases because, again, if you're a producer, typically you want to charge more because you make more money overall. But how sensitive is demand to those changes in price? In other words, if we increase the price of a product just a little bit, what's going to happen? So number one, will the quantity demanded stay the same or say roughly the same? In other words, we could say that demand is not very sensitive to changes in price. If we change the price, if people are still willing to buy roughly the same amount, then demand is not especially as sensitive to price. Or will those changes in price result in a significant drop in how much people are willing to purchase? So which one is it? That's the question we want to answer. If we change the price, what's going to happen to how much people are willing to buy? Is it going to stay roughly the same, or is there going to be a major effect on how much people are willing to buy? Because of course, if the demand decreases, if the quantity demanded decreases, then even though we're probably charging more, we may not make as much money overall because there's not going to be as many purchases. So we have to keep in mind that changes in demand also lead to changes in revenue. We want to maximize our revenue. We want to make the most money possible. We want to charge more in general because that means we tend to make more. But if we charge too much and people are no longer willing to buy the product, then our revenue can potentially decrease. So in analyzing elasticity, we're trying to find the sweet spot. What's the sweet spot for pricing where we're pricing a little bit higher, we're maximizing our revenue, but we're not pricing so high that people are no longer willing to buy our product, which again would lead to a drop in revenue. So what is that balancing point there in the middle? So let's look at an example just to analyze this concept of elasticity. So a Blu-ray rental company has found that demand for rentals is modeled by the following function. So D of X is demand, but sometimes we'll represent it as Q for quantity. So the output for a demand function is quantity, the number of items people are willing to purchase in relation to a price we set. So for a demand function, the input is represented as price. So based on the pricing we set, this function is going to tell us at that price, this will be the quantity that people are willing and able to buy. So in this case, our demand function is Q is equal to 120 minus 20x, where again, Q is the number of rentals per day, so the number of purchases at X dollars per rental. So the input is the price, the output is the quantity people are willing and able to buy at that price. So we want to analyze the effect of each of the following price changes on what the company's revenue would be. And keep in mind, anytime we talk about revenue, in general, revenue is going to be the price we charge multiplied by the quantity that's purchased. So once we get to revenue, keep that in mind. It's how much we charge per item multiplied by the number of items that are being purchased. So suppose first off that prices are set at $2 per day and then increased by 10%. So the idea is we want to know what would revenue be at the current rate of $2 per day, and what would revenue be if we increased price a little bit. What's the effect on how many items people are willing to purchase? And then what's the transitional effect on revenue based on how that potentially changes? So what is the demand at $2? Well, we're going to use our demand function, and we're going to input a price of $2. So the demand at $2 is going to be 120 minus 20 times 2. There we go. And of course, if you need, you can plug that into the calculator. 20 times 2 is going to be 40. So 120 minus 40 is going to be 80. Well, 80 what? We're talking about quantity purchased, and in this case, what we're purchasing is Blu-ray rentals. So that would be 80 rentals. So in other words, at a price of $2, in general, we expect to have about 80 rentals per day. So revenue at $2. In other words, how much are we making if we end up with 80 rentals? Well, our price is set at $2 and we have 80 rentals. So our revenue is going to be our price of $2 multiplied by the quantity of rentals, which is 80 in this case. And so that's going to give us revenue of $160. So when we set the price at $2 per day, we expect to have 80 rentals, and the resulting revenue, taking $2, multiplying it by the quantity of rentals, is going to be $160. Well, what happens if we increase the price by 10%? The question is, how is that going to affect demand? In other words, what's going to be the change in terms of how many people we expect to rent these Blu-rays? And then what's the subsequent change in revenue based on the fact that we may have a change in the quantity demanded? So what happens if we increase the price by 10%? Well, number one, we need to know what 10% of that original price would be. So if we take $2 and multiply it by 10%, otherwise known as 0.1, that means we're increasing the price by 20 cents. So we're starting at a price of $2, and then we're increasing by 10% of that, which would be 20 cents. So if we take 20 cents and add on the $2 we're already charging, that means we're charging $2.20 per rental. So what's going to happen to demand? Well, in general, we expect the quantity demanded to go down. If we charge more, in general, fewer people are willing to purchase our product. But how much is it going to go down? That's the question we want to answer. So demand, when we charge $2.20 per item, is going to be 120 minus 20 times $2.20. Okay, let's plug that one into the calculator. So 120 minus 20 times $2.20. Okay, and that's going to give us 76. So again, 76 what? 76 rentals. We're talking about the quantity of purchases, in this case the quantity of rentals. So notice by increasing the price, we go from 80 rentals and we decrease to 76 rentals. So 4 fewer rentals we expect to take place if we have this price increase. But overall, the price increase may be worth it. So even though fewer people are willing to rent, we're also charging more. So if the increase in what we're charging offsets the decrease in rentals, we still may make more money overall. So what's the revenue in this situation? Well, our revenue in this case is going to be based on our new price that we're charging, which is $2.20. And now we expect a quantity of 76 rentals. And so if we multiply those two together, $2.20 times the 76 rentals we expect to have, that's going to be $167.20. So notice in this case, revenue went up. So we're charging more, which means people aren't willing to buy as much, but the increase in price offsets that decrease in quantity, which results in higher revenue overall. So in other words, it would be good business sense to make this increase because it results in higher revenue overall. Well, now let's look at another situation. So same setup, but suppose we're setting prices at $4 per day for rentals. And then what happens if we increase from 10% starting at a level of $4? Well, number one, what is the demand at $4? In other words, how many rentals should we expect if we're charging $4 for each of those rentals? So the demand at a price of $4 is going to be 120 minus 20 times 4. Well, 20 times 4, that's going to be 80. So 120 minus 80 is going to be 40. So 40 rentals. So notice we're charging more. We're charging double what we originally charged, and our quantity has dropped by half. We went from 80 rentals expected at $2 to 40 rentals expected if we're charging $4. What about our revenue? So if we're charging $40, or we expect 40 rentals and we're charging $4, what would the revenue be in this situation? Well, in this case, we're charging $4 multiplied by the 40 rentals we expect to get. And then 4 times 40 is going to be 160. So notice in this case, we expect to make the same amount of money if we charge $4, resulting in 40 rentals, just as much as if we charge $2 and have 80 rentals. So in this case, the starting revenue level is going to be the same, either charging $2 or charging $4. But the question then is, what's going to happen if we start at $4 and then increase from there? So starting at $2 and increasing, notice we saw an increase in revenue because again, the higher price was offsetting that decrease in demand. But what happens if we do the same thing starting at a price of $4? So if we were to start at a price of $4 and increase by 10%, well, what is 10% of $4? So start at $4 and then 10% multiplied by 0.1, that's going to be 40 additional cents. So increasing this price by 10% means we're charging an additional 40 cents. And added to the $4 we already charge, that's going to be a rate of $4.40 per rental. So if our price increases to $4.40, well, what's the resulting demand going to be? So the demand at $4.40 is going to be 120 minus 20 times our price, $4.40. If we plug that into the calculator, 120 minus 20 times $4.40, and that's going to give us 32. So notice again, rentals went down, which is to be expected. Now, before we look at revenue, let's just analyze what happened in the first situation versus the second situation. So in the first situation, notice increasing the price by 10%, we lost 4 rentals. What about this situation though? We went from 40 rentals to 32 rentals. So in this case, increasing the price by 10% resulted in a larger drop in the rentals that we would expect. So how is that going to affect the revenue, given that we increased the price, but now we lost more rentals than we lost based on a similar increase in a different situation? So let's see what the revenue is going to be in this case. So we're charging $4.40, and based on that price, we expect 32 rentals. So what should we expect in revenue? So 32 rentals times the $4.40 that we're charging and we expect a revenue of $140.80. So notice in this case, our revenue dropped. We dropped by approximately $20. So even though we increased the price, that was not enough to offset the decrease in demand, the decrease in the quantity demand, the decrease in the number of rentals we would expect to have. So in this case, increasing the price by 10% would not be a smart business decision because we end up losing enough customers that our price increase cannot offset. So the ultimate question is, what should we be charging? What is the optimal rate to be charging so that we have the highest revenue possible? We're charging just the right amount so that we maximize our revenue and we're not losing too many customers to the point where we start losing revenue. What's that sweet spot in the middle? And elasticity, the function we write representing elasticity, is going to allow us to analyze that. So elasticity, again, the general idea is how sensitive is demand to the price change. When we enact a price change, what sort of effect does that have on the quantity demanded? Is it a relatively small effect, like it was in this case? Or is it a larger effect, like it was in this case? What's going to happen at different levels of pricing? And that's what we call elasticity, how sensitive our demand is to changes in price. So to generalize elasticity for all the different prices we could charge, we create a function. It's going to be a function of price. In other words, it's going to take price as an input, and it's going to model how things change, how sensitive the demand is to those changes in our input of price. So elasticity is labeled with a capital E, and it's going to involve the derivative of our demand function. So we're going to assume our demand function is d of x. We need to take its derivative, and then elasticity is defined as the following ratio. So there's a negative out front, and then we have a numerator and we have a denominator. So the numerator is going to be x times the derivative of demand, and then that is divided by just the original demand function. So it's important to keep in mind what the input is in this case. In most cases, when we're talking about a financial formula, a financial function, the input is quantity. In this case, when we talk about demand, or talk about this new function elasticity, we're talking about an input of price. So we're outputting something related to quantity. We're inputting price. Price is something we have control over as the producer. We choose the price to set. So we're choosing a particular price, and we're using these functions to analyze what's going to happen from the consumer's point of view, what we can expect in terms of purchases if we set things at that particular price. So elasticity is a ratio, and the ratio means something very specific. It's going to relate percent change in quantity, in other words, the quantity demanded, the number that people are willing and able to purchase, to the percent change in price. So the change in price is what we have control over. The change in quantity, that's determined by market factors, and the elasticity is going to tell us, well, what kind of change in quantity should we expect if we make specific changes in price. So let's practice finding an elasticity function, and then I'll show you how this is used. So consider the demand function that we just looked at, which was d of x is equal to 120 minus 20x, and we want to find each of the following things. So first thing we want to find is the elasticity function, which is given by this expression. So notice again, the elasticity function is going to require that we have the derivative of our demand function. So that's a good place to start. Start by finding its derivative. So the derivative of our demand function, we can just find it using the difference rule and then the power rule. So 120 differentiates to 0, and then negative 20x differentiates to negative 20. So the derivative of our demand function is going to be negative 20. So once we have that, we can plug that along with our actual demand function into this expression, and the result is going to be our elasticity function. So the elasticity of X, again, where X represents the price that we're setting, is going to be negative X times our derivative, which is negative 20. And you'll notice I'm putting the negative into the numerator. You can leave it out front. I just tend to put it with the numerator so that these two negatives can then combine. So that's honestly just personal choice. And then our denominator is going to be the original demand function, 120 minus 20x. And then I just need to simplify all of that down. So multiply the two factors in the numerator. Notice they're both negative, which means the whole expression is then going to be positive in the numerator. So we end up with a 20x in the numerator, and then a 120 minus 20x in the denominator. Now we're almost there. We cannot cancel the x's because that's not a common factor shared among all three terms. However, notice we do have a common factor of 20 involved in each of the terms. So I'm going to factor out a 20 in the denominator, factor it out from both of those terms, and so that's going to leave me with a 6 from the first term, and then a negative x from the second term. And so that 20, that factor of 20 in the numerator reduces with the factor in the denominator, and we're left with x divided by 6 minus x. So this ratio represents our elasticity. It tells us if we make a particular change in price, well, that's going to affect the denominator. The resulting change in quantity is defined by the numerator when we actually plug in a value and evaluate the elasticity function. So in order to better understand what this function is going to tell us, let's use the function with a couple of different inputs. So let's find the elasticity at x equals 2 and x equals 4. Well, what do these things actually represent, these inputs? Well, remember our input for demand is price, and therefore our input for elasticity is also price. So 2 means $2 and 4 means $4. So essentially we're analyzing the elasticity of our demand at the two original prices that we looked at on the previous page in the previous example. So what is the elasticity when we charge $2, when our input is 2? So I'm going to sub that into my elasticity function. So my numerator is going to be 2, and then my denominator is going to be 6 minus 2. So that's going to be 2 over 4, which reduces to 1/2. So in analyzing what this means, we want to interpret what this number is telling us. Remember, think of the denominator as representing a change in price, something we can control, and the numerator represents the resulting change in quantity, which is something that we can't control. So what the ratio 1/2 is telling us is it's telling us, if you might think of it this way, if we change price by 2 parts, that's going to result in a change in quantity demanded by 1 part. So in other words, a small change in price, typically a small increase in price, is going to result in a smaller change in quantity demanded. So in other words, at a price of $2, demand is not especially sensitive to changes in price. We can change the price to a certain degree, but the change in quantity demanded is automatically going to be smaller than that. Now, what about the elasticity at a price of $4? So same kind of thing, plug it in. So 4 divided by 6 minus 4, which is going to be 4 over 2, which reduces to 2 over 1, or typically we just write that as 2. It may be helpful here to think of it as 2 over 1 though, because we do have a ratio. We're comparing two values. So again, the denominator represents how we're changing the price, and the numerator represents the resulting change in the quantity demanded. So what this ratio is telling us is that if we change price by 1 part, then we can expect a change in demand resulting that's double that essentially. So in other words, for a small change in price, we have a larger change in quantity demanded. In other words, at a price of $4, we'll find that the quantity demanded is more sensitive to changes in price. If we make a small change in price, we can expect a larger decrease in how much people are willing to and able to buy. And we saw that on the first page, right? So at $2, increasing the price just a little bit, we actually increased our revenue. So although we lost some customers, the loss of customers was offset by that additional amount we were charging. And so there wasn't a large enough change in the quantity that people are willing and able to buy in order to sort of present a problem for us. Whereas when we were charging $4, that change in price resulted in us losing enough customers that we were also losing revenue. So at $4, our demand is more sensitive to our changes in price, and at $2, our demand is much less sensitive to our changes in price. So the question then is, if at $2 we have an elasticity of 1/2, at $4 we have an elasticity of 2/1, where do we have an elasticity exactly equal to 1, or think of it as 1/1? Where do we have a location where the change in price will be matched by an equal change in quantity demanded? In other words, where are we balancing our change in price and then our change in quantity demanded? Think of that as the balancing point. Well, where does that occur? What is the value of X? What is the price that would result in us balancing our pricing changes and the quantity demanded that we expect based on that change? So we want to know what value of X would make our elasticity equal to 1. So I'm going to take the elasticity function and I'm going to set it equal to 1. So X divided by 6 minus X is equal to 1. Now I want to solve for X and I have a rational equation. So typically a good rule of thumb is go ahead and get rid of the denominator. So if you were to multiply both sides by 6 minus X, that's going to move it over to the right hand side and we no longer have to deal with the numerator and denominator. So if I multiply both sides by 6 minus X, I get X is equal to 1 times 6 minus X, which is just 6 minus X. And then I want to solve for X, so combine your like terms, move the negative X over. So we get 2X is equal to 6, and if we divide by 2, we're going to get X is equal to 3. Well, X is equal to 3 what? Remember, for our demand function and for our elasticity function, we're inputting price, the thing that we can change as a producer. And so it's going to be $3. That is going to be the price we would charge where elasticity is equal to 1. In other words, small changes from that price in $3 result in essentially equal changes in how much quantity is demanded by our customers. So that represents essentially the sweet spot where we're balancing changes in price and what we could expect in terms of changes in demand that result from that. So let's take it one step further. Next thing we want to find is the revenue function. So we looked at demand versus the resulting revenue on the first page. Let's look at that more in general. So our revenue function in this case is defined as X times our demand. So remember, revenue is always defined as your price you charge times the quantity. Well, again, normally when we write a revenue function, we think of our input as being quantity, how many units we make and then sell. In this case, our input is price. X represents price, and then D of X, remember another label for that was Q, Q representing quantity. So price is our input because that's what we're controlling in this case, and then Q, our quantity, is represented by our demand function. So our revenue is equal to X, whatever the price is that we're charging, multiplied by our demand function. Remember, our demand function is 120 minus 20x. So that represents the quantity that we expect to be able to sell at our particular price that we've chosen to set. So we're going to multiply x times 120 minus 20x. That, of course, means x needs to be distributed into parentheses. So that's going to be 120x minus 20x squared. So that function reflects what we can expect to make in total revenue based on choosing a particular price. So x is our price, we plug it in, and this total amount is going to be the dollar amount representing our revenue. So the last question we want to answer is, what is the price that we would set that would maximize our revenue? In other words, we want to find the location where this function is maximized. And we've spent a lot of time doing that at this point. So remember, we're going to differentiate our function, take that derivative, set it equal to 0, and then solve for x, which is going to give us any critical values that this function has. Critical values represent those locations where we may have a maximum for our function or where we may have a minimum for our function. So we want to find those critical values in order to determine where that revenue is going to be maximized. So we need to start with our derivative. So r prime of x, take our derivative for our revenue function. So 120 for the first term, minus, bring down your 2, so 40x. So there's our derivative. That function tells us how our revenue is changing. So we want to determine, where is the derivative going to be equal to 0? Where do we potentially maximize our revenue? So in this case, we only see the x one time. There's no exponent. This is linear, so there's only going to be one value of x that solves this equation. All we have to do is isolate our x. So I'm going to add the 40x and move it over, and I'm just going to go ahead and switch sides. So that would give us 40x is equal to 120. And then if we divide by 40, we get x is equal to 120 divided by 40, which is 3. Well, 3 what? Well, remember, our input now represents price. So $3. And that number looks familiar, right? Where else did we see that number? We saw that number right here. So the price at which our elasticity was equal to 1, in other words, changes in price and changes in quantity are balanced. That also happens to be the price that we would set in order to maximize our revenue. Now, it's worth double checking to make sure that this does in fact represent a maximum. So remember, let's draw the sign chart. We want to determine what's happening on either side of this critical value, what's happening to the derivative. If we were to look at the actual function, is it sloped upward, is it sloped downward, what's happening on either side of that critical value in order to confirm that we do in fact have a maximum. So let's plug in the function for our derivative. So 120 minus 40x, and I'm going to graph that. And I'm zoomed way out, so I'm going to go back to zoom standard. And there we go. Okay, so there's the critical value at 3. That's the one location where this function is going to cross the x-axis, where the whole function is equal to 0. And then notice to the left of that location, our derivative is positive, which means our function would be sloped upward for values less than 3. And then once we cross over, we're below the x-axis, which means our derivative is negative, and our function would be sloped downward. So we go from being sloped upward to peaking to then being sloped downward. So $3 does in fact represent the location for the maximization of our revenue. And again, it is not a coincidence that these two numbers are the same. If we balance pricing with the quantity we can expect to have purchased by our customers, that's also going to be the location and the pricing at which we maximize our revenue. So let's formalize that a little bit more. So what is the relationship between elasticity, the sensitivity of our demand to how much we price our product at, and what we really care about, which is revenue, the money that we're making? Well, we can officially say that revenue will increase. In other words, we can continue to improve our revenue at those X values where our elasticity is less than 1. So at these values, we would say that demand is inelastic. In other words, making changes to our price, making small changes to price, result in relatively small changes to the quantity demanded. So we saw inelasticity with the situation where we were looking at $2 versus charging $2.20. So notice we had a small decrease in the quantity demanded, but the additional price we were charging offset that, and so our revenue was continuing to increase because we were charging more, we weren't losing a ton of customers. So at those particular values, we say demand is inelastic because overall the changes in price don't result in major changes in the quantity demanded. And so for those particular values, we would say revenue is increasing. In other words, again, we can continue to improve our revenue. Now, total revenue is decreasing at those values where our elasticity is greater than 1. So at these values, we would say that demand is elastic. In other words, it is very sensitive to the changes we make in price. And we saw this situation with the pricing at $4. So remember, at $4, we also made $160 in revenue. But when we increased the price by 10%, we lost enough customers that that price increase didn't offset what we were losing in revenue. So we lost money overall. So because we ended up losing money, our demand is sensitive to price. It is sensitive to price in the sense that if we continue to lose customers by pricing our product at a higher amount, then we're also losing revenue. So if we're increasing our revenue at specific values and then decreasing our revenue at specific values, so increasing, think of that as your revenue function is sloping up, decreasing, our revenue function is sloping down. As we know, there's got to be a maximum somewhere in the middle. So if we go from increasing to decreasing, there's a maximum in the middle. Where is revenue maximized? Well, as we saw from that previous example, revenue is going to be maximized at X values where our elasticity is equal to 1. So when our elasticity is exactly equal to 1, we say that our demand has unit elasticity. Unit elasticity. Unit meaning 1. Whenever you see the term unit in math, unit typically means 1. So unit elasticity. In other words, we've balanced the changes in price to the resulting changes in quantity. We're not at the point where we could be charging more, where we could improve our revenue, but we're also not at the point where additional charges would make us lose so many customers that we start losing money. This, whatever X value gives us unit elasticity, that represents the sweet spot. Whatever price gives unit elasticity, that's the price we want to charge because that's the price where revenue is maximized. So graphically speaking, if we look at our demand function, again, demand and price are inversely related to one another. So if we price things low, demand is high. People are willing to buy a lot of our product. If we price things high, then people aren't as willing to buy the product, so the quantity demanded is low. Somewhere in the middle is the sweet spot where our elasticity is equal to 1, where we balance the changes in price with the changes in demand, with demand's response to those changes in price. And as it turns out, if we look at our revenue function, which we know will increase to a certain point and then decrease from there, it just so happens that the price where we have unit elasticity and the price where we maximize our revenue, they are the same. They occur at that same price. So how does this help us? Well, if we want to analyze our revenue and determine what is the optimal pricing in order to maximize our revenue, to have the best outcomes possible for the business, we can analyze revenue directly, or we can analyze our elasticity function. If we know what our demand is for our product, we can model the relationship between price, the price we set, and how much people are willing and able to buy. Then we can form our elasticity function, and wherever our elasticity function is equal to 1, not only have we balanced our changes in price and the resulting changes in quantity, but we've also found the sweet spot for pricing where we know we're going to maximize our revenue, we're going to make the most money overall. So let's apply this with a new example. Okay, so given the demand function, Q is equal to D of X is equal to this particular function, so we have a radical function, the square root of 300 minus X, we want to do a few things. So first thing, we want to find the elasticity function. We're going to start there. We also want to take this and find the value of the elasticity if X is equal to $250. In other words, if this is our price, is demand elastic? In other words, it's very sensitive to additional changes in price, or is it inelastic? In other words, it's not very sensitive to changes in price. And then also we want to find the value or values of our input, X, which again represents price, where we maximize our revenue. In other words, what is the optimal pricing so that we can balance out, ideally, the customers that we may lose if we increase our pricing with the actual price we charge in order to make the most money possible. So we want to start with our elasticity function. So let's write down the formula for that. So the elasticity of our demand is equal to negative X times the derivative of the demand function divided by the original demand function. So we need to start with our derivative. So I'm going to come over to the side and we'll work through that. So the demand function is equal to the square root of 300 minus X. So this models the relationship between our price and then the quantity we can expect customers to purchase based on setting that price. Now we know in order to differentiate something like that, typically when we have a radical, we want to write that in exponential form. So the square root of this expression would be the same thing as raising that expression to the 1/2 power. And now we're in a position to be able to differentiate. So the derivative of our function is going to require the chain rule. So we have a function inside of another function. So we take the derivative of the outside function, leave the inside function plugged in. So here the outside function is a function with an exponent. So bring down the exponent and then decrease the exponent by 1. And then don't forget, when we use the chain rule, we have to multiply by the derivative of the inside function. So 300 differentiates and goes to 0. Negative X, its derivative is going to be negative 1. So that is going to be the derivative for our demand function. Now don't spend a ton of time manipulating this right now. All I would say is really worth doing is maybe go ahead and multiply those two constants together. So that would give us negative 1/2 times 300 minus X to the negative 1/2 power. And we'll just leave it like that for now. We're just going to plug it in that form, and then we'll see what needs to happen once everything is substituted into our expression for elasticity. So let's plug it in. So negative X, I'm going to put the negative with the X. Now we're multiplying that by the derivative that we just found. So negative 1/2 times 300 minus X raised to the negative 1/2 power. And then we're dividing all of that by our demand function. Now we can put in the version that has the radical, or since we already have a negative exponent in the problem, let's put it in its exponential form so that we're comparing things that are similar to one another. So I'm going to plug it in the exponential form. So 300 minus X raised to the 1/2. Okay, so now it's just a matter of cleaning things up, seeing what we need to do from there. So the first thing I'm going to do is, I don't especially like having that 1/2 in the numerator. Now notice we do have two negatives, just like we did the last time, and so those are going to multiply together to give us a positive. But I don't especially like having that 1/2 in the numerator, so I'm going to factor it out of the whole expression. I'm going to pull it out front, and I'm just going to write it out front of everything. So that's going to give me 1/2 times everything that's left. So what's left from there? Well, we still have the x in the numerator, and then we have the 300 minus x raised to the negative 1/2, and then all of that is divided by 300 minus x raised to the positive 1/2. Okay, now let's deal with that negative exponent. So we know a negative exponent means we could also just flip it and move it to the denominator, and then the exponent would become positive. Now what's that going to leave us in the numerator? Just an x. So we have 1 times x times all of this moves, so we're just left with the 1 times x. And I can go ahead and move that 2 into the denominator as well, and then I'll just have one fraction. So I'm going to write the denominator first because it's a little bit larger. So 2 times 300 minus x raised to the 1/2, that was already there. And then this one, apply that negative exponent, which flips everything and moves it to the denominator. So 300 minus x also raised to the 1/2. And then we have an x in the numerator. Okay, so notice we have two things that are like. We have a 300 minus x raised to the 1/2, and then we have another one, same kind of thing. So we can approach what we need to do here in a couple of different ways. It may be a little bit more intuitive at this moment to go ahead and change these back to square roots, so we're a little bit clearer on what we're working with. So I'm going to go ahead and change those two expressions back to radical form. I'm going to rewrite my denominator. So 2 times the square root of 300 minus x times another square root of 300 minus x. And then we have our x in the numerator. Now we can see those two matching square roots. So square root times itself, well, anything times itself is just that thing, whatever that happens to be, squared. So if we were to take a square root and square it, well, squaring and taking a square root, those are inverse operations, which means they cancel one another out. So what's going to happen from there? Well, we multiply these two together, square root squared cancels, which just leaves us with that 300 minus x. So we have our x in the numerator, and then we have a 2 times 300 minus x in the denominator, and we can leave it like that. That's fine. So if we wanted, we could distribute the 2, that would be fine, or we just leave it like this. So notice our elasticity function doesn't involve anything that's a radical, and that was just based on how the derivative and the individual function were actually related to one another. So this is going to be the function that models how our changes in price affect the associated changes in the quantity demanded. So we have our elasticity function. So the next thing we want to find is the value of the elasticity when x is $250. And specifically, do we have demand that's elastic or demand that is inelastic? So we want the elasticity with an input of $250. If this is what we charge, what is the elasticity? So I'm going to plug that into the function. So our numerator is going to be $250, and then our denominator is going to be 2 times 300 minus $250. Now you'll notice we have dollars on top and bottom, which means when we simplify this down, those units actually cancel one another out. So elasticity does not actually have a unit, it's just a ratio of like quantities. So the dollar signs are going to cancel out, and we'll just be left with a ratio, just a number. So our numerator is going to be 250, and then our denominator, 2 times 300 minus 250, is going to give us 100. So $250 divided by $100, and if we simplify that down, 250 divided by 100 Well, there's the decimal version. Let's convert it to a fraction. So math, arrow fraction, is going to convert it to a fraction of 5/2. So what does this mean? Well, this means if we were to change price by 2 parts, that results in a 5-part change in the quantity demanded. In other words, a small change in price will result in a larger change in demand. In other words, our change in price has a major impact on the change in the quantity demanded. So that implies that our demand is elastic. It is sensitive to price at a price of $250. So from a more practical standpoint, that means we're probably pricing things too high. If we increase the price from here, then we're going to lose too many customers and we're going to lose revenue overall. So if $250 is too high, well, what's the right pricing? What's too low? What's too high? What's the right pricing? So the next thing we want to determine is the values of X, maybe 1, there could be 2, the value or values of X where revenue is at a maximum. So remember, revenue is at a maximum. We determined that that was going to occur at the same price where elasticity is equal to 1. So wherever we hit unit elasticity, that particular pricing also results in us maximizing our revenue. So we don't have a revenue function here, but we do have the elasticity function, and so we can determine at the price at which our elasticity is at unit elasticity. So we're going to set our elasticity function equal to 1. Well, here's our function. So we're really setting x divided by 2 times 300 minus x equal to 1. So similarly to before, we're going to multiply both sides by our denominator, move it over so that we don't have a numerator and denominator. We just have one side equal to another. So that's going to be x is equal to 2 times 300 minus x. So just multiplied, move that denominator over. Okay, now we'll probably want to distribute the 2. Okay, so that's going to be x is equal to 2 times 300, which is 600, minus 2x. Now we're going to add the 2x, move it over, combine the like terms. So that gives us 3x is equal to 600. And so if we divide by 3, we get x is equal to 600 divided by 3, which is 200, and more specifically, $200. So $250 is too high. $200 is just the right pricing. If we want to maximize our revenue, that's the pricing that we would set to maximize our revenue and also to offset our price changes with those changes in quantity. That's going to be where those two changes are in balance. So $200 will be the optimum pricing for this product, at least just looking at revenue. So this is going to give us just another way to use the derivative. So we've looked at several different ways we can use the derivative in the context of real-world situations. So analyzing demand is something that's very important within a lot of different business contexts. Using the derivative and then using the derivative to find this elasticity function allows us to analyze the situation involving demand.